we'll tackling one of the significant challenges in Kubernetes is intelligent autoscaling. If you are running EKS clusters in production, you faced questions like how do I restrict traffic without reservation? How do I leverage spot instances without sacrificing reliability? How do I ensure that I'm only paying for the capacity that I'm really using? And these are not theoretical problems. We are facing this constantly, and it's good news that we have tools like Karpenter to resolve this issue or solution. So let's begin. What we're going to discuss today is why autoscaling matters. You'll see the business and operational impact on the scaling perspective. Kubernetes scaling overview. You'll understand some basic. You'll remind ourselves of basic or native options that Kubernetes provides to scale. We'll see what is its core components and capabilities. We'll see also an alternative to Karpenter, a new solution that AWS provides. Then it will be some demo examples. We'll see some provisioning scenarios, and then we'll see some tips or some decisions that may impact our deployment. And lastly, is questions. So let's start. Consider a realistic scenario. It's 2 a.m. and service experiences a big traffic spike, like 10 times than usual. Pods starting scaling and there is no capacity. You start queuing and be pending on the schedule. What happens next? It's possible to log in AWS console and provision manually 20 new instances, and that not really bad. So our SLAs may be already degraded because of that. Other scenario is when there is a batch analytics jobs in a cluster that runs. They execute once 1 hour at night and then scale back down. And without automation, we can just over provision capacity to have it running 24/7. This is expensive solution. You'll lose performance if you do not provision enough resources. And same for developer-driven deployments as well. So a fundamental issue is that we cannot manually be ahead of the load of our infrastructure and capacity and use manual scaling. That's why auto-scaling really matters. What of native solutions in Kubernetes? We have horizontal pod autoscaler is a tool or resource that monitors metrics like CPU or memory utilization, and when this matrix reaches threshold, it creates additional replicas. When utilization drops, it scales down. This is straightforward and handles application level. And we have nice vertical pod autoscaler. It analyzes actual resource usage of this pod And for example, if you requested 4 CPUs, but using one, then vertical pod autoscaler adjusts this request to use to downward. And in capacity of the cluster, we have cluster autoscaler, which supported in almost. And how it works is just to watch the pods that cannot be scheduled on some capacity, or we have insufficient node capacity. Then it detects some pending nodes and provision new nodes. However, it have some limitations. It uses poles to detect when we need to scale. It runs 1/10 fold, and scaling is tightly coupled with node groups, which is predefined instant types, and it handles spot instances very poorly. And it has no consolidation as well. This tool works as basic scenarios, and for modern production clusters, we should have more modern solutions for that. For modern limitation we have with cluster autoscaler is slow scaling. We need to have instant pod provisioning. In ideal world, it should be in seconds, not minutes. Response should be immediately after pod cannot be scheduled event. Also, we should utilize spot diversity and fallback logic. For example, is exhausted in the availabilities on region, then let's try to move to C5 instance. When C5 unavailable, let's use T3. So it's better always to maintain forward progress. Also, we need to have multi-architecture support both ARM and x86 workloads without manual node group switching. We should prioritize spot over on-demand instances. Select most cost-effective instances that meets our requirements. Also, we should have automatic consolidation. When demand decreases, automatically consolidate workloads to fewer nodes and terminate idle capacity. With the cluster autoscaler, it's not possible one efficiency. That's why we have Karpenter as a tool to fix all of that and meet our requirements. What is Karpenter? Karpenter is open source, high performance Kubernetes cluster autoscaler that provisions compute resources in real time based on application requirements. What does it mean is not provisioning is in seconds, not in minutes. Karpenter watches for unschedulable pods and responds immediately. And comparing to cluster autoscaling, which uses polling approach. Automatic instance selection. Specifically, if you are selecting, like, if you are running the gigabyte and Karpenter evaluates all compatible instances and considers many aspects like cost, availability, interruption rates, etc. And it selects most optimal choice. Also, it maximizes spot economics by supporting many compatible instances simultaneously. Karpenter enables in spot instances, and it really simplifies operations. You can focus more on the application optimization than on infrastructure optimization, because Karpenter have a lot of capabilities and have a lot of complex consideration under the hood. Let's see how it works. We see the Karpenter controller is deployed in EKS clusters. Usually it's like several pods that can be run on Fargate nodes, and it uses two custom resources, node pool, where we put all logic of the all our rules, how we want to deploy, provision instances, and actual configuration of the of that EC2 instances that we want. It speaks is Kubernetes scheduler to see in real time all events, all pods that cannot be scheduled, and that allows to immediately respond. And it speaks with the EC2 Fleet API to provision EC2 instances as fast as possible. Also, it uses SQS to events when some spot instances become unavailable. So it also can react to that as fast as possible. So how it works in this picture. In this picture, you can see that we have some existing resources that deployed on two instances, and we want to deploy like 3 pods capacity, and it can detect that one bigger node can be much more cheaper than utilizing 3 smaller EC2 instances. Then in result, it
Sorry,
migrates.
Vlad,
Yeah.
I have one notice about freezing the video because of lack of electricity. That's why we have such problems.
Yeah, sorry, I just got electricity. I may reconnect if it's. Let me reconnect. Can you see my screen again? Cool. So when I was interrupted, so Karpenter used just-in-time capacity, and it provisions capacity that is most cost-effective at the time. So we can see that instead of using many small instances, it can provision one bigger if it sees this can be much cheaper. Let's dive deeper in the configuration that we have. For node pools, we can define rules that can set instance families that we want to use, the scheduling constraints like tains for the nodes that we provision, labels that it should have, not selectors, limits for availability zones, etc. We can also set scaling behavior, how much it should scale over the time on or scale down as well. Consolidation policy, we can use some aggressive scenarios when it starts to consolidate instances as soon as it see um, option to save costs. But in some critical production setups, we should be more conservative, like wait for some time and like have some timeouts for that as well. We can set node expiration configuration, for example, uh, to get latest security patches that we got. So by default, recommended option is 21 day. We can set more or less for that as well. In EC2 node class, we can define the infrastructure that we want to provision, like instance image that we want, some bottle rocket images, EKS optimized images as well. We can set security groups, subnets configuration, and tags, IAM roles. We can set custom user data for this EC2 instance, or we even may use some custom kubelet configuration. It also have some legacy in some clusters, probably maybe seen before version 1. It was some old abstractions like provisioner, which was replaced with node pools, and AWS node template, which was replaced with node class. My favorite feature is consolidation. So after traffic spike, uh, uh, we have usually some unused node capacity, and most of the scalers leave these nodes running indefinitely. But Karpenter continuously evaluates whether workloads can be consolidated into like less nodes. When consolidation is possible, it cordons an underutilized node and gracefully relocates all pods to a different node and then terminates it. This is great bin packing optimization that happens automatically with Karpenter. So, as I said, we can use more aggressive or conservative options for that as well. For capacity optimization, Karpenter decision engine doesn't simply pick available instance that it can be provisioned. It evaluates many signals like spot availability. It takes real-time data from the region. Um, um, sorry. It takes pricing of the instances and its families. It takes also into consideration the interruption rates that happened historically in the cluster that we used. It combines all these factors and select instance that balances cost, availability, and stability. And it's usually very fast. Also, it supports flexible instance selection. So we are not only restricted to M5 large or C5 large. You can specify family that you are okay to deploy a provision instance like M5, C5, T3, etc. And Karpenter evaluates all compatible options that are best for the time. If one instance family becomes unavailable, it seamlessly shifts to different family without blocking any pods. Also, it have graceful spot interruption handling. So when AWS sends termination notice, it's 2 minutes before interrupting the spot instance. Karpenter receives the signal and marks a node as unavailable to schedule new pods. And it gives by default like 30 seconds time to gracefully shut down pod, but we can also extend it to 2 minutes as well. And it beforehand provisions a replacement node to relocate this pod without like major failures to do it smoothly. Also, Karpenter exposes a lot of metrics that can be used for observability. For example, this is a default Grafana dashboard that we can find in the library. And it exposes a lot of metrics like limits, a lot of how many pods are scheduled, distribution of the pods, distribution of the nodes. We can set the alerts for the limits when coming to the threshold. Also, we can build some more complex and custom dashboards. For example, this one from a previous project that we used, Karpenter. You can see like on top graphs the how many disrupted nodes we got, how many nodes was created or terminated, and much more. You can see at the bottom the node pool that we set and how many resources are used as well. So let's compare two options that we got. So not provisioning speed in Karpenter, it's no choice. It works much faster, almost in seconds compared to cluster autoscaler. Instance diversity. We do not limit it to only the specific node type that are in the node group selected. We can just select the node families that we are okay, and Karpenter selects the best choice for us. Spot support. Karpenter also handles interruptions very efficiently. It does not require node groups, and it has consolidation. Also, it supports GPU and Gravitron instances as well, and it can use both of them as well. And it's very flexible to select compared to cluster autoscaler. For clusters autoscaler, we need to provision a lot of node groups, and it adds more complexity for setup. So what also we have compared to Karpenter, we can use the EKS auto mode. What is EKS auto mode is we can think of it like AWS managed Karpenter. It uses it under the hood, and it's almost same autoscaler. But with auto mode, we do not manage this autoscaler. We do not configure policy, not classes. We can just deploy our workloads, and AWS handles capacity automatically. So here is a list that Automod handles. by default, we can just deploy EKS EKS clusters with automod, and we can just deploy anything we want. It already ready to be run. Let's see some benefits. So it can be literally no YAML setup. We may skip configuring node groups, node pools, node classes, AMIs, or Bootstrap config. So AWS handles everything. And actually, AWS Automod is an evolution of the shared responsibility model that AWS provided in 2017. Back then, we said we'll manage our control. AWS said we manage your control plane, and you manage your nodes and application. But with Automod, AWS manage all data plane too. So we can think what it means that AWS owns configuration for that. No need to hand tuning launch templates. No need to mm, bother with patching of the EC2 instances. AWS uses manages it itself. Also, AWS repairs instances and manages auto-scaling as well. And while also using Automod, it allows us to use some custom node pools and EC2 node classes, but configuration is limited compared to bare Karpenter. We can customize node behavior. We can create node pools in scenarios like we need to a specific instance type, for example, which by default we are not okay with the default configuration of Automod. We need to isolate some workloads for security reasons or cost tracking purpose. Also, you can configure ephemeral storage like some IOPS optimized size and throughput for the instances. But we do not have option to change image of this EC2 instance or login actually by SSH or session manager to that image. AWS manages it and restricts it. And it's really easy to just install it add-on to EKS cluster. Let's compare all of the options that we have. So EKS Automod, it's really easy to use. We can just install add-on and be ready to run. In Karpenter, we need some configuration, but it's much easier to configure cluster to scalar with node configuration. Node management in cluster to scalar, we need to manage and create some workarounds to handle spot instances, termination, etc. In Karpenter, everything is out of the box, so it can manage, it can detect some issues and migrate all the resources to different and healthy node. In EKS Automod, we have almost no option to manage our nodes. Same for control. In Karpenter, we have very high control. We can select almost any option that we need to modify. And for spot strategies that I said in Karpenter is very high. You can select best strategy for ourselves, but in EKS Automod, AWS manages it by itself. So when to use Automod? If you embrace almost no ops solution and managed infrastructure overhead is not what you want, it's okay. If your workloads are stateless, ephemeral, like microservices, API, web apps, it's also a really great choice. If you have priority to do fast iteration over detailed control, it's also nice. If you're running GPU workloads, it's also nice, but it's not very custom. Karpenter great if you are using some stateful application, if you need persistent storage, if you need some deep customization, some custom AMIs, specific OS versions, or specific or specialized instances, then Karpenter is a great choice. If you are invested heavily in the reserved instances or saving plans, then Karpenter is also great. And it also allows us to set up very complex cost optimization rules. When you should avoid one or another option, Automod is not okay if we need some persistent storage because beyond default options. If we really need some specialized images for EC2 instance, that's not possible to do with EKS Automod. If we are using reserved instances, then it's also not a choice. When to avoid Karpenter? Karpenter is not a choice if we have um, if you have mindset to set it and forget it. Sometimes it requires some optimization. If we don't have operational maturity to tune consolidation, constraints, limits, pods configuration, etc. But overall, it's a great choice. Let's maybe do some demo, and I'll show my different screen. Mm. Yeah. Mhm. I've created the simple EKS clusters, EKS cluster in my account using the blueprint in the in this repository. Terraform AWS EKS blueprints. It's bare minimum to run everything that we need. What I want to deploy first is EC2 node class. It's default configuration with just bottle rocket images. And node pool. Let's see a configuration of node pool a bit closer. We can set the labels for the nodes. We should use reference to EC2 node class that we created. We set expiration configuration option for this node. So after 14 days, the nodes will be recreated. Termination grace period is also when we have some pods that cannot be terminated. It has some like pod distribution budget or something else that does not allow to evict pod from the instance, then it will be forced after this time. We can set our requirements for instance that we want. For example, we filtered old generations from the families of instances we have. We allowed the instance category C, M, and R. Also, use AMD 64 architecture, and capacity that we want is on demand. We can set limits, how many CPUs and memory we want to have maximum. And last one is disruption policy. It can be when empty or when empty or underutilized, and timeout for this action. Let's apply. Yeah, and I have EKS node viewer to see instances that we have. For now, we have no pods that should have some instances. I have just two forgate nodes for Karpenter controller and two forgate nodes for core DNS. And I want to filter it to use node selector. Okay, and let's deploy something. Let's see. It's a simple deployment with a image pose and nothing much. Yeah, and let's scale it. For example, let's add one replica, and we should see that it already created a EC2 instance on demand C6 large, and there is two diamonds, and there should be one pod, which is our. Let's scale it more. Let's make it seven replicas, and we'll see that it started provisioning 2x large instance. It has 8 CPU cores, and we should be able to fit everything, all 7 of them, in that instance. And after consolidation timeout, we should be able to see that it disrupted our first node and moved everything to the bigger one. You can see it here, or but here is better. You can see it's already disrupted, and all pods already on the new one. So it handles auto-scaling the cluster very fast, and you can see that it's efficient. Maybe let's do some more complex setup. We can use weights for node pools. For example, we want to have a different node pool that is higher on priority than other ones, and it has some additional configuration. For example, I have weight node pool with weight 2, and we use here instance capacity T. So it will start to provision nodes with this capacity using this node pool because it has higher priority. But if instances from this family is not available, then it start provisioning in the other node pools that is possible to utilize. You can see that it was created, and let's scale our instances and our deployment more. Let's do 15. We should see T instance here. Yeah, immediately started the instances that can fit all of them. But it not disrupt existing one. If you want, you can drain this node and it will reschedule everything on the T instances. Okay, it's okay. Let's do some cost optimizations that we can utilize in the Karpenter. Maybe let's scale it to 0. No, let's do 7 to have one instance. No, sorry. 0, and let's delete latent or pool. When I delete node pool, it start to delete all the instances from that node pool as well. And now we can scale. Okay, and in the cost optimization scenario, we have option to what I did is I extended the selection range that we can use. I did IRM chips, IRM processors, and spot instances. Also, in addition, we can filter out the not instance types that we do not want to utilize. And let's do it. We'll filter this one and add IRM and spot instance. It will select the better option. To do that, yes, and we have now conflict between pools because they have same weight, and it should be not. It's recommended to not have conflicted or overlapping node pools. Yes, and now we'll see that it starts. We start to delete these instances, and it will provision a new one. Maybe in optical. Oh, let's restart. Usually, I should delete it. That not pull default one first. Um, let's see. Not a problem. Sorry. Focus. None of who's available. Ah, it's not applied. Sorry. That's why. Okay. So we have instance, a spot instance, and cheapest option, this setup as well. We can also limit the CPU, how many CPU we should have on this node pool, for example, at 10. And if I schedule more than 10 instances, it should not deploy them. Again, 15. 9 of them should be running, and rest of them are unscheduled. But it uses this instance which have 15, so it's not disrupted. It applies on the next iteration, actually, so that's why. If we do drain, it should create a new node, and it should use this limit as well. But first let's remove this limitation. Yeah, Karpenter sees it as disrupted, removes it, and it should start a new node. Yes, and you'll see. Yeah, and 9 of them are running, and the rest are unschedulable because we have a limit of 10 CPUs. Let's move on and try to scale everything down to make it fresh. And let me delete after it's not. So what we have in other option, you can use a split. For example, if you want to have ratio 4:1 on demand and spot instances utilized for our what we can use something like capacity spread key, and you can select like 1 here and 4 additional values for spot node pool. And let's let's apply it at C and see. Split not full. And we have deployment that uses topology spread option. So it utilize the capacity spread key, and let's try to deploy it as well. And in this scenario, which we should see 5 nodes, and it should have one on-demand instance and 2 spot instances. If you deploy 10 pods, it will be same ratio for this setup. You can see it already running as we want. What else? What else we have? We have topology spread deployment, which want to be deployed on different availability zones. If you'll see, if you'll check the nodes and the labels that it have a lot of labels that was provided by Karpenter and Kubernetes, and we'll see the availability zone, like availability zone 1, and utilizing this topology spread, we can deploy all of them in the different availability zones. Let me delete previous deployment. Now let's apply. It should replace. Yeah, and now you should see new pods and nodes that are on different availability zones. And it also uses the topology spread for this config. Okay, you see that nodes are deleted, pods created. Let's see. Nodes. One node have availability zone 3. Which one is next to delete? Have 3 pods, but let's wait for disruption. It's 30 seconds set. But it should really be in different availability zones. Not full. 30 seconds. Yeah. On demand is deleting because it's costly, and should be one more. When it's deploying, let's see the other options that I can use. We can use if we have some resources that we do not want to evict, or when some deployment is deployed on the instance and we want to keep it and do not disrupt it in any scenario. For example, it's like a very critical component of our system. We can set annotation to Karpenter, do not sure. So with this annotation, it will not disrupt. We can do, let's see, we have 3 instances from previous example, and if we check all of them, availability is on easy one. We have 2 availability zones. Here is 3. Yeah, anyway, let's scale down our deployment to 0, and let's create a node pool that recreates instances every 2 minutes. It will be last example. It drops these nodes, and in this example, we'll create a similar node pool, but we'll have expire after set to 2 minutes. So it will recreate all nodes after 2 minutes of this existence. Node pool, and this deployment. We should see the new nodes and the pods with this label, this annotation. Here is a new node. And it has all this, all 4 replicas. Let's wait for 2 minutes, and you should see that this node will not get this disrupted status, and it will not be recreated. We should see the Kubernetes events regarding this as well. I see some questions or messages in the chat. Let's see. No questions. So 1 more minute, and it should be here. Let's see, and events.
Still we're waiting. Can I have some questions? Can you hear me?
Yes, guys, ask your questions.
Sorry, I do not hear anybody. One moment.
Oh, okay. Now you hear me,
Sorry,
right?
no, I had a problem with my headphones, and
No worries, no worries. Till we're waiting, I have one questions.
Yeah.
How hard to switch to use Karpenter your EKS cluster? Because I didn't use the Karpenter. For now, we have like default EKS in AWS. But I'm curious, is it worse or how hard to switch to the Karpenter? Or it's easier to build new EKS with Karpenter from the very beginning?
Actually, there is some nice documentation in AWS itself it have every step to switch. And is it good to switch? It's more like more flexible way to save costs and optimize our nodes to this. So it may be worth considering to switch to this. And complexity, it depends. It may be some already like hard dependencies on the cluster autoscaling, or maybe some limitations on the I've seen some limitations in autoscaling and load balancing and um, and what and networking probably, but it depends. It depends on the complexity, and I don't know. Maybe it worth to switch. Is it okay? Is it the right answer for you? Or
Yeah. Thank you.
okay, we can see that this node wait, probably I have said wrong annotation. Annotation do not disrupt. One moment. Yeah, probably I misconfigured something here and it's still disrupting. That's my bad. Anyway, let's go back to the presentation and continue. There's last several slides, and we already spent more time than expected. So what else we have? We have some tips for that, and it may optimize configuration. For example, if we allow diverse instance types, it in this case it may drastically optimize the costs, and in case if some type of instance is not available, then it can be used as a backup plan. If we can configure consolidation very aggressively, then we may see some issues. If you have some pods that have no limits on memory, for example, Karpenter will see that these pods uses a specific amount of memory, and will schedule it on the node that have, for example, 4 gigabytes node, 4 gigabytes of memory, and you'll see the big burst of the requests. It may exceed the limit, the amount of memory on the instance that it will be killed. So in this scenario, we can set some more less aggressive configuration for consolidation. We could also set the limits and billing alarms for the resources. For example, we can limit the amount of nodes that can be provisioned, and we can limit some resources that can be on these node pools. And you can also create CloudWatch alerts when we hit the thresholds for these limits as well. That can help us to reduce some problems. We can use some layered constraints and fine-grained scheduling. For example, if if you have some GPU job and that requires instance with GPU, we should select a specific node. We can use node affinity to select specific nodes with the GPUs enabled and or restrict the specific post deployment of these nodes on node pools. So it may help us as well. So also we can tune the spot handling. We can update the graceful termination period for the pod and extend it if it's really needed. We can subscribe to signals that Karpenter sends inside of clusters and be ready to be evicted gracefully. And common pitfalls and most issues that are happening is some missing IAM roles and some misconfiguration here. Subnet selectors should also consider should we have configuration that have correctly set all the selectors as well. If you have too strict requests in the node pool, then we can miss many opportunities to reduce costs by using different cheaper nodes. For example, if we exclude some node instance families, that it may also be less less flexible if if this other instances is not available as well. So yeah, same for our constrained instance types. We can use spot instances, but if we have spot instances that are unavailable in this region, we will not be able to deploy anything on this node pool as well. Pod distribution budgets also may cause issues because Karpenter considers distribution budget, and when and for some critical services, if we want to have high availability, we can see simultaneous disruptions, and they will not be gently moved to a different node. So in this scenario, pod distribution budget should have some limitations, how many pods should be available at a time. So it will create this step-by-step eviction from different nodes. And tight affinity rules can break the bin packing. For example, if there is some middle between big node, a small node, and there is pod that is between these requests, and if you have affinity rules that spread everything on different nodes, it may be hard to optimize cost as well. And that's it from me. Thank you for joining, and if you have any questions, please tell.
Guys, do you have any questions? So I suppose no questions. So Vlad, thanks a lot for your presentation and for sharing your experience with us. Thanks all of you for joining us today. We hope this presentation was useful for you, and you will receive a feedback form shortly. Please fill it out because your opinion matters for us. So guys, have a nice day. See you soon. Bye.
Thanks, everyone. Bye.
Thank
Bye.
you.
you.
Amazing
Bye-bye.
demo. Have a great day. Bye.
Thank you.